This is for those of you who have not been in class that have been struggling a bit with section 2.5, and looking at my notes is not enough to help you understand. So I'm going to do some miscellaneous problems. I'm going to do 2 and 3 together, and then I am going to include Descartes' rule of signs, which is the other handout, 2.5b, as part of the process when I solve these two problems. So I'm going to jump right down to number 2 here. And the first thing you have to understand is that P and Q are factors of the constant term and the leading coefficient. And the reason they're important is because the ratio of P over Q gives you a list of what are called possible rational zeros. It's a way to do synthetic division using a narrowed down list of values so that you can find a zero that is going to work. And so the possible rational zeros are going to narrow down that list. And so P will always be a factor of the constant term. So in number 2, that would be factors of 9. And Q would be factors of the leading coefficient, which would be 2 in this case. So what I'm going to do is list out the factors of P, which the factors of 9 would include 1, 3, and 9. Then the factors of Q would be plus or minus 1 and plus or minus 2. And they're both positive and negative because zeros can be either positive or negative. A zero that is positive is a zero that is to the right of the origin. Remember, zeros are where the graph crosses the x-axis. And zeros that are negative are zeros to the left. So here, P over Q, which I'm going to write here, if you take each P factor over the Q factor of 1, that's going to include plus or minus 1, plus or minus 3, and plus or minus 9. And then if you take each P factor over 2, that's going to add to the list plus or minus 1/2, plus or minus 3/2, and plus or minus 9/2. Now, my objective here, I'm going to change the color, let's go with that, is to find one of these possible zeros that's going to work when I do synthetic division and gives me a remainder of 0. So as I look at my polynomial, I don't have any missing powers, so it looks like I can go 2, -11, 12, and 9. And remember, in synthetic division, you drop down the leading coefficient, and we're looking for a remainder of 0 if the number we test is going to be a 0 of our function. Now, I could go through this one at a time and just start trying values. Like, for instance, if I try positive 1, that would be 2, -9, -9, 3. I can see it's not going to work. And so I need to start over and try a different value. And, oops. This is where if you have access to graphing technology, which anyone can get a graphing app on their iPad, you could speed up the process by looking at where the graph crosses the x-axis. But if you don't have that, you just go +1, -1, +3, -3. And I happen to know that +3 works, so I'm going to go with 3. And 3 times 2 is 6. When I add, that's -5. That gives me 15, which is somewhere I missed something. Oh, no. Oh, -15. That's -3. And then this would be -9. So what that means at this point is that, oops, I'm in my classroom and the lights just went off. Okay, so the factored form of my polynomial would have to include x minus 3. I know that because 3 actually was a 0. I found that when I did my synthetic division. And then the 2, -5, and -3 are 1 degree less than my original polynomial. So up here, the degree is 3. So 1 degree less would be degree 2, which would mean I have 2x squared minus 5x minus 3. You always want to do this until you reach the quadratic level, degree 2, which if it's a cubic function, you should only need to do 1 synthetic division. If it's a quartic, degree 4, like number 3, we're going to have to do 2 consecutive synthetic divisions to be able to reach the quadratic level. At this point, we want to set the polynomial equal to 0, which I'm having a little room, so I'm going to go up here for space. And if I let my factors equal 0, I need to solve the quadratic to find the other zeros. Of course, we know x would have to equal 3 when I set that factor equal to 0. That's obvious. That's why we tested it. The other factor is quadratic, and my hope is that this is going to factor. If it doesn't, then I get to use quadratic formula. So I'm going to put 2x and x. I know 3 and 1 are the only factors for the last positions. I need the difference since this is a minus. The difference of our outside and inside product need to be 5. So I'm going to put the 3 here, so that's 6x. The 1 here, so that's 1x. And 6x and 1x have a difference of 5x. And then I want to put my minus there and my plus here. And so if I set each of these factors equal to 0, I think most of you probably recognize this is going to give you -1/2. But I'm showing you full steps. And then here, I think you know we get x equals 3 again when I set that equal to 0. So my zeros, which in my math lab are going to be in set notation, would include 3 and -1/2. I don't need to list 3 twice, although what I do know is the multiplicity is 2, since there are 2 of those zeros that are 3. And it also means the graph would be tangent to the x-axis at 3, whereas it would cross the x-axis at -1/2. So that's what you're doing in solving these problems. Let me show you Descartes' rule of signs with this problem. Descartes' rule of signs is going to have me look at the signs of my answer. Now I'm going to erase a lot of this so I have room to write. I think this will give me enough room, hopefully. All right. If I need to erase more, I will. Let's go with a different color. Let's try green. So I'm going to, Descartes' rule of signs, the green handout, the other page, has you count the number of sign changes in both f of x and f of the opposite of x. Sign changes of the coefficients, meaning if I look at f of x, the first coefficient is +2 and the next one is -11. That's a change in sign. Then from -11, I go to a +12. That's also a change in sign. +12 to +9, they're both positive. So the changes in sign of f of x give you the number of potential positive real zeros, zeros that are positive numbers, like 3 that we just got in our problem. So I counted 2 sign changes. The funky part about this is the theorem says, or is less than this by an even number. What that means is you need to subtract 2 from that number, and 2 minus 2 is 0. I wouldn't subtract 2 again because then I'd get a negative 2, and you can't have a negative number of zeros. So just bear with me. I could have either 2 positive real zeros or 0 positive real zeros. Now I have to find f of the opposite of x. Anytime you put in the opposite of x and raise it to an odd degree, that's going to change the sign of your answer and the sign of the term. So for instance, negative x when you cube it is negative x cubed, times 2 makes it negative 2x cubed. The next term, when you put in negative x and you square it, it's still going to return a positive, times the negative 11 means it remains negative 11x squared. Then positive 12 times negative 1, x to the first is odd degree, so that changes the sign of the term, and then the constant term's not going to be able to change. So you have to find f of the opposite of x to figure out how many negative zeros you can have. So I look at the sign changes of my coefficients, negative 2, negative 11, no sign change, negative 11, negative 12, no sign change, negative 12, positive 9, 1 sign change. So for negative real zeros, I put positive, but I meant negative, I only count 1 sign change. If I subtract 2 from that, it's negative, so I can only count 1. So now this is where my little chart, if you looked at my other handout, comes into play, and you might have been confused, which they don't use this in my math lab, but I use it, and I think it's a good way to keep track of the outcomes of your zeros. Our zeros can be positive, negative, or imaginary. If a zero is 0, we actually factor it out first, so we don't have to worry about that. So remember, I counted for positive real zeros, 2 or 0 zeros, and for negative real zeros, I don't know, this stupid thing, my light keeps going off. For negative real zeros, I count 1. So I need to do all combinations. I need to do 2 positive with 1 negative, or I need to do 0 positive with 1 negative. Now, the column for I is the imaginary roots. You have to understand that the sum of the positive and negative and the imaginaries has to add up to the degree, which we said was 3. So each row in this chart has to add up to 3. So if I would have 2 positive real zeros and 1 negative, that already adds up to 3, which means if that were my outcome, that means I have 0 imaginary. That is actually the outcome that I have here, because look at your zeros. Your zeros are positive 3. There are 2 of them because the multiplicity is 2, and negative 1/2. So you have 2 positive real zeros, 2 3s, and 1 negative 0, which is negative 1/2. So we're in the first row. That's what our chart helps us to understand. The second row, if we have 0 positive and 1 negative, that would imply we have to have 2 imaginary so that the row adds up to the degree of 3. We're not in that row with our solutions, but that's what the outcome would be. Now, this chart, back in the day when we didn't have graphing technology, was really useful because, for instance, here, either row says we're going to have a negative 0. So that might reduce the number of synthetic divisions you'd have to try until you got a remainder of 0. Now, with technology, I say check the graph and use one and then do synthetic division. Hopefully that explains things. On the next problem, I'm not going to do the whole smash, but I am going to get you started here. So let me move this up to number 3. And we're going to start with the P over Q. P is a factor of 13. Q is a factor of 1. So the only factors of 13 are 1 and 13. If Q is a factor of 1, when you take each of these values over 1, you have the same values. And so I'm going to suggest anytime Q is 1, your P factors are also your P over Q factors. So if I look at this problem, and if I looked at the graph, I would find that the only value that works is positive 1. And the graph's actually tangent at positive 1, so it should go in evenly. So I'm going to write 1, negative 6, 22, negative 30, and 13. If it's a 0, obviously it goes in evenly and the remainder is 0, which I already know. That's why I'm testing it, because I looked at the graph, which is just shortcutting doing like synthetic division with each value. And you can see, of course, it works. Now, what that means is 1 is a 0, we tested it, and then the depressed polynomial that results from doing the synthetic division, the coefficients really imply 1x cubed minus 5x squared plus 17x minus 13. But that's a cubic, and we're not to the quadratic level again. Now, I could write a second synthetic division separately, but I'm actually going to piggyback on my first. And when I do synthetic division, I'm going to have one less column. That last column drops off because I'm only working with the cubic. And again, I'm looking for a remainder of 0. So I've got 1, negative 4, negative 4, 13, and of course, it works. So at this point, I've done 2 consecutive synthetic divisions. So my polynomial, f of x, would be the quantity x minus 1 times the quantity x minus 1. I'm going to write that as the quantity squared, since there are 2 factors of negative 1. And then what results, the first synthetic division took me from a quartic to a cubic, and the second synthetic division took me from a cubic to a quadratic. So this becomes 1x squared minus 4x plus 13, and there's my polynomial. Now, if I'm solving it, I'm going to let this be 0 and, get all my solutions. We know 1 is a solution, and it has a multiplicity of 2. The quadratic, the only way you're going to solve it, because it's not factorable, is quadratic formula. And just so you understand that, I ended up, when I solved it, my zeros were 1 and 2 plus or minus 3i. You can look at my Canvas slide to see this and how you get it, but that kind of gives you a feel for it. I hope that helps. And I'm going to finish this because I've been talking way too long. Hope you have a good day. Let me know if you have questions. Thanks. Oops.